we have a very interesting panel set up here today. The topic is the changing fleet in the future. We have four very expert entrepreneurs, I would say, that are trying to change the way the fleet looks in the future with different classes of vehicles, looking to do some current missions in a different way and maybe some new missions or even some re-emerging missions that once were that have disappeared and may re-emerge. So they're all working through their vehicles and the various challenges, and they obviously see opportunities. And I think we'll just jump right into it. We have the next 90 minutes. The way we're going to run this is each of our panelists will have time to give introductory remarks, and there will be a QR code like you've seen all week to be able to ask questions, and I'll work through those questions as we're able, as many as we can. So let me go ahead and introduce the panelists that we have here today. I think we have a chart on each one of them. Do I have a clicker?
Maybe the clicker.
There we go. So our first speaker will be Aleksey. I'm going to pronounce it right. Matyushev from Natilus, who's the CEO and co-founder. The next speaker will be Heironimus. I'm butchering it, I'm sorry. Vice President of Engineering at Otto Aviation. The next speaker will be David Lazara, Staff Scientist for Applied Aerodynamics at Boom Supersonics. And then we'll finish up with Peter Schmidt, the co-founder and COO of Transcend Air. We're going to dive right in with Aleksey. I'll turn it over to him. Sorry for butchering the name.
So welcome, everybody. Thank you so much for coming over to this. The idea behind what we're about to show you is the idea of different vehicles. And of course, there's going to be a separate discussion behind it. What Natilus was founded about was the idea that we introduce a blended wing body. I know it's been embodied in a lot of different ways, but we believe that we actually have the right idea and the right market traction to actually go do it. So if you look at the blended wing body design, it was, again, super headed between McDonnell Douglas and NASA in the late 1990s. There was a lot of fundamental challenges behind it. One of the biggest challenges behind it was stability and control. What Natilus actually brings to the table is we believe that we actually have been able to figure it out. This is my favorite slide of the entire deck. So if you look at the industry as a whole, we're challenged, to say the least. So the original 737 was designed, built, and flown and certified in 3 years. In 1967, it took $1.1 billion in today's dollars. So the next CEO of Boeing came out and said that it's going to take $50 billion for us to get there. So there's a huge gap in the market. So as technology has gotten faster and better, there's a huge gap in the market of how we actually get it done. At the same time, like what we believe fundamentally is that the airlines have, for some reason, changed the tune. And might I add, so if you were to buy a Boeing or an Airbus airplane today, it's going to take 12 years for the customer delivery. So we buy 12 years into the future. So that, coupled with a duopoly, along with the idea that there's actually sustainability challenges, which is everybody wants to be sustainably neutral by 2050. For the first time ever, the airlines are actually willing to listen to startups such as us. As a company, we want to be a large OEM. We design, build, test, and certify our large products directly against the Boeing products today. So the blended wing body, of course, has a revolutionary idea. We have validated a lot of this data, but I want to focus on two numbers that really don't get a lot of traction. The first one is, of course, the 30% aerodynamic drag. We all believe in that. But what nobody actually talks about is the volumetric capacity of it. So 40% more volumetric capacity. That's for air freight, and that's also for passengers as well. What actually comes down to is the idea that we can actually produce per kilo or per pound 50% less reduction per passenger seat mile or per pound. What Natilus is focused on today is two products. The first one is a Kona regional freighter today. 4 metric tons meant for the likes of UPS and FedEx. And then we want to scale up into the 200 passenger market with the Horizon. The big idea behind this chart is there's a huge question mark in the entire industry that over the next 20 years, 40,000 brand new airplanes have to be built. Boeing has only got capacity for 11,000, Airbus for 15,000. And so the entire industry and the airlines are asking, like, where is the next 15,000 airplanes are coming from? We also believe that this is also a dual-use technology. As we think about the Indo-PACOM region, there's a lot of what we do today actually is able to scale down into the Indo-Pacific region for logistics and all sorts of stuff as well. So let's talk about the Kona. The Kona is our first product. It's a blended wing body meant for regional delivery, carrying 4 metric tons. It's able to reduce the cost per pound by about 50%. We already found traction within 50% of the, I would say, the Marriott flight fleet, which operates 180 airplanes for UPS today, as well as Laminar as well for austere environments up in Canada and the like. Our second product is the Horizon. We can't announce a lot of customers behind this, but we found 100 and 200 and 300 airplane orders behind this product as well. We truly believe that this is going to become a revolutionary idea as we scale up the company as well. One of the ideas that is really interesting behind the entire industry is the idea that Boeing has created a lot of, I would say, like Japanese or anything else like that as far as environments for scaling manufacturing. We want to scale everything here homegrown. And we're partnered with Palantir to actually help us grow and do this. At our steady state environment, we want to produce 1 737 per day, 365 days per year. And with that, I'll hand it over.
Thanks.
All right, thank you. Good morning. Let's see. All right, let me tell you the story about Otto. So, for us, practical implementation of laminar flow is the name of the game. And that started with the Celeron 500 aircraft. Let's see if this will play. Whoop, nope. Could you click play for me? There we go. Excellent. All right, so Bill Otto Sr. built this aircraft in a cave with a box of scraps. No, sorry, that was Iron Man.
That was Iron Man.
My bad. But for us in the industry, it felt like that when this out of nowhere practically rolled out of the hangar in Victorville. There were spy photos of it. People were asking, what the heck is this thing? Is it a military project? Is it something secret from one of the OEMs? Instead, it was one man's vision to make laminar flow a practical reality. And when you do that, what that can do to the industry. So one of the, okay, there we go. So flight test in 2019 of this aircraft, we flew about 60 hours of instrumented flight tests to collect data. We did collect a significant amount of data, and one of the most telling pieces was the gas receipts, the fuel receipts. So you'll see that Piper Navajo was our chase plane. It was flying with thermal imaging technology to view the laminar flow on the aircraft. One of the most shocking things was after flying back-to-back with those aircraft when they landed, and we went to go refuel them, how much fuel had been burned in each aircraft. We, of course, have the data of why that's the case. And a lot of folks have said, well, we haven't heard much from Otto. This thing flew, what happened to the whole thing? And the answer is, well, in 2019 we flew, and in 2020 was this thing called COVID, right? So everything went quiet for a little bit. We started looking for investors, and by 2022, we had found folks that were very interested in the technology, but wanted to apply it into a different space, a different mission. So that led us to our jet performance, or our jet aircraft. So the laminar flow technology that we proved on the 500 was spectacular from a drag reduction, However, as you want to go longer range, there's a desire to go faster, and there's a desire to have 2 engines. So that is just a natural progression into a twin jet. And what we found when we applied the technology was that we could make a super mid performance jet, so an aircraft that had a super mid-sized cabin, stand-up cabin, 9 passengers, with a cruise range that can go coast to coast. But instead of doing that at 35 to 40,000 pounds, we can do it at 19,000 pounds, which obviously saves cost from a manufacturing standpoint, but more importantly, saves a huge amount of fuel and cost from an engine reserves. So how are we doing this? How are we getting a 40,000-pound jet performance at 19,000 pounds? Well, the first piece of that, of course, is the aerodynamics of the drag reduction through heavy use of laminar flow in the aircraft. We proved that on the 500, and we have been actively working to transition that into our jet configuration. Dr. Tom Wayman's in the audience here somewhere. He gave a presentation on our transonic wind tunnel testing on Monday. So the data is starting to be out there of how we're actually doing this. What we found in the wind tunnel test for our jet was really spectacular performance in that 30% drag reduction range. So the question then becomes, well, if you have a 30% drag reduction, how does that turn into a 60% fuel burn reduction? And that comes back to designing a clean sheet aircraft. So right here is a little chart out of the Breguet range equation. And what you'll see on here is that most of your super mid aircraft that have that 3,000, 3,200 mile, 3,500 mile range, they all burn fuel in the 250 to 300 gallons per hour range. That's your BNCA or your JSSI data for that, right? A 30% improvement in your lift to drag efficiency actually brings you down, because it's a nonlinear equation, right? It's exponential in the Breguet range equation, brings you down to a 60% fuel burn reduction. So that puts our performance with a super mid cabin better than a light, a mid, and super mids from a fuel burn standpoint, which of course is, for business jet operations, fuel burn and engine reserves are your main drivers of direct operating cost, so makes a spectacular big business case. The other thing it allows us to do is get into twice as many airports. So our balanced field length will be less than 3,500 feet, which is in the same ballpark of other light jets. We're the weight of a light jet. We have the engines of a light jet. We have the field performance of a light jet even slightly better because we have a nice big wing on the aircraft, which opens up far more airports that we can fly into as well with that super mid performance. And then, of course, from a fleet and sustainability standpoint, there's a huge opportunity for global warming reduction, and really, and interestingly, in 2 places. The first, of course, is in carbon emissions reduction. So if we burn 60% less fuel, there's 60% less carbon itself. Burning less fuel allows us to have a business case that we can start to afford more use of sustainable aviation fuels as well in the existing cost framework of the business jet market. And then a really other interesting thing happens is that we can see our best performance with our laminar flow airfoil at high altitude. So we like to fly 45, 47, 51,000 feet. And something really interesting happens up there is that the air is too cold and dry to form contrails. And there's been many studies recently that show that from an induced heating standpoint or a global warming force standpoint, the contrail development is actually potentially even a larger contribution than the carbon emissions themselves. So Otto's approach here allows us to very quickly reach the 2050 Paris Accord goals. So we save cost, we open up the market into more airports, and we have the opportunity to significantly reduce global warming forces. Thank you.
David.
I want to first say good morning to all of you. You brought a lot of excitement and energy on the last day of the conference, and so I tip my hat to you for being here. That's an accomplishment in and of itself. We've had a fantastic time here this week. I have joined Boom back in August, coming from Boeing Research and Technology after 12 years in advanced aero design, working a variety of concepts, including high-speed aircraft. When I transitioned to Boom, I found an opportunity that was unique out in the industry, and I'm excited to share the overall concept of what Boom is trying to offer for changing the fleet by 2050. And as we know, a picture is 1,000 words, so I provided a few videos to give you some context and history of what is the beginning of supersonic flight and how is it going to change in the future. And as we watch the video, the intent is to understand the why motivating the effort that Boom is undertaking.
Airliner of the future, flying at twice the speed of sound, it will hop the ocean in 3 hours.
It's an exciting time to be in the part of the industry focused on high-speed flight. The Overture product aircraft is designed to be a supersonic passenger airplane capable of taking 60-plus passengers over 4,000 nautical miles. Its design is perfectly situated for high-speed performance, while at the same time balancing the important constraints that set apart the Overture airplane to that of Concorde decades ago. Two very different high-speed problems and low-speed problems in these two aircraft. And I'm proud to say that the small team of engineers at Boom have been able to accomplish much in a new approach to designing high-speed vehicles that meet today's regulations and can do so in a way that closes the business model for many, unlike the opportunity of the past where Concorde was not able to do that and meet today's stringent regulations and business opportunities. One of the big enablers to the Overture design is the Symphony engine. And although it might be conventional wisdom to say we don't design airplanes and engines at the same time, it is because of that bold decision that Boom made just a few years ago that we've been able to unlock very large improvements in both performance and use cases for the airplane. If you're not familiar with the status on where the Symphony design is, I have another clip to show you how it's evolved and how we've entered the new test phase. The Symphony program is an ambitious attempt to bring a new engine to market that fits in between existing off-the-shelf options. As a 40,000-pound thrust class medium bypass ratio engine, it is already designed to be 100% SAF compatible so that we can plug that in once the infrastructure is ready for use there. On top of that, it has a key set of design features going from highlight at the inlet to trailing edge at the back of the nozzle that enables meeting the noise regulations as part of the package overall with Overture. We have some experienced partners in the industry that have helped with the turbo machinery design, as well as others who have been a part of engine OEMs and aircraft OEMs who have come together to bring the design in a way that could not be possible by simply pulling an off-the-shelf engine. And that takes me to the first point I wanted to make when it comes to changing the fleet. In my view, the fleet in 2050 doesn't change until we start with the people today that make it happen. What I've seen in my short time at Boom is that the people there are very open-minded to bring their depth of expertise and to expanding that beyond so that we can learn quickly and at the same time, while being mission-focused, incorporate some core principles that enable a very different development process. That involves challenging assumptions we may have had from our prior experiences, looking at requirements and ways to improve them so that we can burn down risk, improve the design in a smart way at the right time in the process, and therefore not excluding innovation, but weaving it in so that we can innovate at scale. That type of thinking requires looking at procedures for design in a different way so that we can iterate rapidly and automate effectively. One of the ways this has panned out is by Boom's approach to disrupting the traditional aircraft development process. As many of you know, and as I experienced previously, the airframe design and the engine design are basically two separate design worlds that are brought together in oftentimes a suboptimal marriage. When Boom made the choice to bring the engine in-house, they essentially brought those two worlds and made them one, allowing for optimal integration, mission performance, and even closure of a business model. This is what sets apart Boom from other attempts at high-speed flight in the past. In addition to changing the development process, we've been very open to embracing revolutionary thinking. With the advent of AI and machine learning tools that accelerate pace, we find opportunities to unlock insights. What seems to be an old problem, we are seeing it through new lenses. This translates into reformulating problems to reveal different Pareto frontiers and enable different trades and decisions that in the past maybe were not possible. And that has allowed Boom to then look at execution at the program level in a way that is also unique, looking at how to blaze new trails by rethinking a traditional progression of a development program, but in a more iterative manner. The attempt at doing this might seem far-fetched if it's never been done before, but Boom took it upon themselves to apply some of these principles with their first flight demonstrator. I have a clip next to show what its first supersonic flight was like, and I intend to convey some of the other opportunities that that demonstrator has now unlocked.
Control your go for Excel to Mach 1.1.
Captain Go for Excel, Castrol Gate.
We found it amazing to see the demonstration of Mach cutoff operations, the type of cruise flight between a narrow band of Mach numbers, between 1 and 1.3, And with the help of our friend the atmosphere, the propagation of pressure waves from the aircraft are oriented in such a way that as they encounter higher speeds of sound at lower altitudes in general, they refract and churn away, reaching an inflection point above the ground. That means that the strong sonic boom and any focusing that is encountered above the ground remain away from you and I, and we're left with much lower amplitude evanescent waves instead. That has created the opportunity to fly 50% faster than today's airliners over land, while at the same time offering the 100% increase of speed over water. Bringing that type of performance and capability to the airspace means innovative routing and operations. That includes sonic boom management, making sure that the aircraft is routed in unconventional ways to keep a strong sonic boom away from the coastline, or managing with the changing atmosphere on a sub-hour frequency using today's technology and future technology to enable Mach cutoff operations. Bringing that together with existing air traffic management approaches is going to be an important step in changing the fleet in the next 25 years. And Boom has been designing the Overture airplane to fit right in to existing infrastructure, requiring no changes in current airports, and simply following the rules of flight, going in from one destination to the other. Lastly, I wish to make the point that the fleet in the future won't be changed unless we do it one enthusiastic passenger at a time. And what we've seen today is that the public is very interested in flying long routes much faster. They are willing to put aside their frequent flyer miles to accomplish this and pay a premium for that speed. So I'm excited to be a part of both the people and the process to make this new high-speed product possible, and I thank you today for your attention.
Cool. Thanks, David. Peter.
Good morning. I'm going to talk about changing the fleet with regard to advanced air mobility in 2050. So I have to start by defining advanced air mobility. Here's one concept, the Jetsons, 1962. This aircraft was powered by anti-gravity. Seagram's whiskey ad from 1943. You'll notice there's already one helicopter landed, and their buddies are arriving in this new wonderful machine. And if you look really closely, you'll see it doesn't have an N number, it has an X number, but it's 1776 to represent the freedom of flight. And that's really what advanced air mobility's dream is about. And there in the city, you can see there's a rooftop helipad with 5 more helicopters sitting there. This dream goes way back. Leonardo da Vinci in the late 1480s and his air screw. That is really the first documented fly-like-a-bird vision from an engineer that we have. Then there's Uber in 2017. Uber came up with this concept, which is formally urban air mobility. And you'll see they've got, I don't know how many vehicles, how many rooftop helipads. There's some sort of STOL aircraft landing there. None of this vision fits with the current regulations or the emerging ones for safe helipad operations. But man, it looks cool, doesn't it? Urban air mobility is a subset of advanced air mobility. Advanced air mobility was first articulated by NASA in this vision statement. Unfortunately, the slide's cut off. Basically, they're talking about not just flying over urban cores, but flying at low altitude with uncrewed aerial systems and drones. What they left out is the thing that I think is going to transform advanced air mobility by 2050 and change the fleet. So if we look at the major technologies shaping the future of AAM, we have things you've heard of: autonomous flight, electric aircraft, eVTOLs, hydrogen aircraft. But the one I'm going to focus on today is high-speed VTOL, because that's where I come from with Transcend Air. This is our VI 421R. That's for reserved edition. It's the VIP one with the Batmobile paint job. This is a tilt-wing, high-speed VTOL aircraft. It is designed for both high agility in vertical flight and to cruise at over 400 knots with a range of up to 1,000 nautical miles. This is designed for RAM, or regional air mobility. So Aleksey showed that chart that has 15,000 airliners missing from production and asked where they're going to come from. And I'm sure Boom is going to fill some of those, Otto is going to fill some of those, and Aleksey's company is going to fill some of those, Natilus. But we intend to fill the orders for a bunch what otherwise would be single-aisle airliners doing regional routes with this aircraft. So that leads me to having this very academic slide that I have to explain to you folks, because I may be the only person in this room who has actually ever run a charter operator of Part 135 aircraft at the scale of the aircraft we're designing. So high-speed VTOL is, I'm a promoter of it because it targets the most profitable routes in aviation. So this is a matrix of origination and destination pairs, and I have noted each square with what type of commercial service is currently used for it. Part 121 is the big airliners that everybody's familiar with. Part 135 is charter, but Part 135 can also be 135 commuter, which looks like airline service. And you'll notice that city to city, that O&D pair is the vast majority of not just the demand, but also the profits in the aviation business generally. So it turns out that high-speed VTOL leverages the point that access to the demand-rich centers of cities is required for high load factors. If you don't have high load factors, you don't make money. And that's one of the things that killed Concorde. You want to maximize seat miles per day to get profitability. And that you can get with large aircraft or with high speed. We focus on high speed because we want to operate out of city centers, out of vertiports, not airports. And now congestion in major cities across the world has gotten so bad, it turns out that high-speed VTOL, regional air mobility, can be price competitive on a door-to-door basis with the sum of ground and airline travel costs. And in the process, will shorten door-to-door trip times by 75%. So high-speed VTOL, regional air mobility, is cheaper, faster, and better. And that's how you revolutionize a market. So we're going to disrupt travel like nothing has since the jet age. So we're talking Manhattan to Boston, 32 minutes in the air, an hour door-to-door, $265 for a ticket price. That's about 12% less than the current door-to-door Uber plus Delta Shuttle plus Uber price for that route. LA to San Francisco, 1 hour, $295. And you don't have to go to an airport. No airports is no congestion. So somewhat in contrast to my colleagues up here, Transcend was actually started on the back of achieving this vision, and we picked an aircraft to suit. There are other aircraft makers that are now moving in this direction. Joby and Archer are both working on hybrid electric designs with longer ranges that can serve this. So as usual, no really good market opportunity has only one player in it, and we never expected that. But I'm pretty confident that our design is going to have a really compelling place in this market as we move towards 2050. Thank you.
All right, thank you all. That's so quite a range of opportunities. I think, well, low speed is relative, but low speed to high speed, and vastly different configurations. So the audience should be able to start posting some questions. But I'm going to just kind of start with Aleksey. You showed 2 configurations. Are you working those in parallel? I mean, they were, one looked like a single aisle and one was maybe a smaller cargo.
Yeah, so I think like from a configuration perspective, if you look outside in, you would say like we're defocused. We're focused on a passenger version, we're also focused on a cargo version. But one of the things that what I think has plagued the industry for a very long time, if you look at the smaller, like the guys who actually can execute, like the Cessnas, the Pipers, and everything else like that, is as soon as you're finished with one program and you kill the headcount, you have to do another program. And so like the way we're thinking about it is we'll start with, one program, we'll increase headcount, but also have the second program, and then we'll actually be able to execute on that. What I truly believe is we're not focused. It's a very strong statement to say, but like we're definitely focused on 2 configurations, but in a thoughtful manner as we look at it together today.
Yeah. Okay. So I'm going to go down the line and just kind of, it may have been in there, but we'll summarize kind of where are each of you now, and when do you expect to see your product enter service so we can fly on it?
So I can't promise anything, right?
I'm not asking for promises of your plan.
I don't think any one of us can promise, right?
Everybody's an innovator, so.
Yeah. We've already started building the first
People wanna fly 'em.
prototype.
People
Yeah.
wanna fly these.
The Kona. We always say 24 months, but it's been 24 months for a little bit, like 6 months, so a little bit late.
Yeah, so from an auto standpoint, obviously we've had the 500 demonstrator flying for a while now for the Phantom 3500 jet. We are about to wrap up our preliminary design phase this year. We are targeting first flight of our FTV-1 in late 2027 and targeting entry into service by 2030, which is generally an aggressive timeline, as we would always want to do, but Otto's been working really hard to make it also a very realistic timeline. I mean, there's a lot of folks out there that are highly ambitious about what it takes to certify an aircraft. One of the things that Otto has really focused on doing with our Phantom 3500 jet development was taking a very straightforward path to certification. Part 23, engines off the shelf. Most of our systems and components are off the shelf or modified off the shelf. Mechanical reversible controls. We're not trying to be the first Part 23 fly-by-wire aircraft out there. So that's a big part of, that focus is a part of why we think that 2030 timeline is achievable.
So the FTV-1, is it a production prototype?
Yeah,
or is it a demonstrator like?
Yeah, so it is, we have 4 flight test vehicles planned for our development and certification program. FTV-1 is really intended to be a performance-conforming aircraft in that we are still designing it with production intent, but there's a few things that you can get going a little faster on if you're not going to try to conform the aircraft. So FTV 2 through 4 would be conforming from a certification standpoint in various levels, as is typical for an aviation development program.
Okay.
But FTV-1 is not intended to be a quick and dirty shed build type of thing. We're actually partnered with our production intent partners across the board from systems and structures, so that aircraft is it's representative to from a performance standpoint, but it's also allowing us to learn in building it, because anyone who's been through an aircraft development or production program knows that even with your best intent, when you build the first airplane, you learn a ton.
Oh yeah.
Things that worked really well, oftentimes things that didn't work very well that you want to go change. So there's time in our schedule between that first FTV-1 build and then when we start actually taking credit for FTV-2 and sub.
Okay, Dave, do you want to?
Sorry, I have a question for the entire panel here, because it's very interesting that actually we're starting to talk about this. One of the biggest questions that I get as far as investors, what does an airplane program cost? And so I have a number in my head, and I'll start up first. I feel like a Part 23 airplane in our size and shape costs between $150 million and $200 million.
He asked, I didn't.
Sure, 10x that.
10x that? Oh my gosh. And Boeing and Cessna, Cessna would be out of business then. That can't be the truth.
Well, I guess it depends on what you're trying to say. If you're a Cessna and you're already established and you've got, okay, I did a helicopter program from an established OEM that cost in the ballpark of what you just talked about.
Are you serious?
It's different if you're established
Will we
versus
all
a
be out of
startup.
business then, man?
No, not necessarily. I think there's still a very strong business case for these
All right,
things.
well,
even
boom. What's your program cost?
If the Boom CEO, Blake Scholl, was here, he might be able to give you a better number than I can. What I do know is our approach has been to look at what are the non-recurring costs that are traditionally making development programs as expensive as they have been. And there are many facets to the reasons behind that. Late discoveries in test, having folks that come in doing a lot of work that maybe now, with the tools we have, we can do in a different, smarter way. And so we're finding that as we look at this question from different angles, we've had a variety of estimates come up. And so I can't pin one down for you right now. I haven't seen them all.
Is it 5 billion?
I actually don't know.
The fact that you don't know is a very strong answer.
So I'll be honest with you because I'm not always in the room for those discussions. But what I can say is we're looking at this from the technical development side of things. With modern tools, how can we be more efficient and faster? Because we have a small team. The XB1 program went supersonic, and if I were to survey the audience to see how many people you guessed were on that program and its cost, You might say 1,000, 2,000, maybe more. Turns out at the peak there were 100 people on that program. That is a completely different paradigm when it comes to aircraft design, and we're trying to carry that over into the Overture. So as important as it is for investors to try to gauge in the long run, we're trying to get ahead of that by the approach. We're looking at certification in ways that I at least haven't seen done elsewhere, again, given new tools, and I know across industry we're trying to reduce the cost of that, but we're being very proactive years in advance to set ourselves up for success to, again, reduce the non-recurring costs. Flight test is expensive. We learned that with XB1. We had, I think, 13 flight tests there, but we were very strategic in what we were trying to test and what the use cases were for the data. And I see now as we transition and have been testing Symphony and are already in the planning stages for testing the next piece of hardware that we fly, I find that we're bringing as much to the table as we can to lower these costs. I've seen wildly high estimates that on a cynical side are easy to believe. I've seen some more optimistic ones. I'm not sure where it's going to fall at the end, but we're doing our best to get ahead of it instead of being naive about the realities we're facing in the economy, investor interest, and what we can do with the resources we have.
All right, so we'll let Peter answer the
$350 million.
$350 million. Very specific.
I love it.
So the answer comes from a couple of combinations. I'm very respectful of the risk in developing and certifying a new aircraft. I shifted career tracks into aerospace 15 years ago as the president and COO of a Eclipse Very Light Jet operator. Does anybody here remember the Eclipse Very Light Jet? That program cost $1.2 billion, produced 260 aircraft, of which I was operating 7. When you look at what the cost was to certify and get that into the market, the investors paid about 30%, the supply chain paid 70%, and the average price of those aircraft was nearly $8 million. Of course, the customers were only paying 2 or so, the supply chain ate a huge amount, as did the investors. So we've been motivated as a North Star to avoid that. Now, our aircraft is in fact more complex than an Eclipse 500 because we have a fly-by-wire flight control system, triply redundant. It's necessary to achieve the performance with the tilt wing we want. So in order to limit our risk, we've used off-the-shelf components and a proven vehicle architecture that we have innovated and improved upon. The tilt wing vehicles flew in the 1960s very well. The XC-142 went over 400 knots the year I was born in 1965. So we're bringing that back, but with improvement. So where a lot of our risk has been is in the flight dynamics and the flight control system, and we've now burned that down substantially through work funded by AFWERX Agility Prime and in partnership with the VSDDL at Auburn University, and that's what I was demoing earlier this week. So if anybody came and got a flight in our flight sim and saw our hardware-in-the-loop subscale aircraft, that's what you were experiencing. So getting back to Aleksey's point, we worked with our friend Richard Abbott early on to size this. And when we look at our certification program and we look at the history, the database he has, that's where the 350 comes. There's some distribution around that number. It's probably not much on the low side, but hopefully nowhere near the $1 billion that Eclipse did way back when.
That billion was in what year's dollars?
Oh, wait. So
Yeah,
Eclipse was supposed to be the biggest failure of general aviation in the history of general aviation.
Yeah. Yes, so we need to beat that.
And the reason why it became a failure, I'll be more than happy to offer my ideas behind it, but it was ran by a software engineer.
Well, and he believed the Williams jet claims. Williams claimed literally off-the-chart weight performance numbers that they couldn't deliver. They had to re-engine the aircraft as they're already in flight test. So that's really what added up.
All right. Let me come back to my original question for now. Current target for when we can fly on Boom?
That's right. The target for Boom is still the end of the decade. We have plans to fly hardware again prior to that, and that's what we're transitioning from. We've just wrapped up what we consider the conceptual design phase. And when you look across the Overture and Symphony programs, we find a spectrum of maturity at the subsystem level, the configuration level. And so we're seeing that over the next few years, we'll be able to reach another level of maturity where we can look at flying hardware again. And just like was mentioned previously, the intent there is to learn very fast by actually doing it. In the air, the experience there, the data we gather is so different sometimes from what we expect from prediction, as good as the tools are these days for prediction and design. But we are not naive to the fact that we need to be in the air as soon as we can and as often as we can. So that's still the main target. With the Symphony program in a parallel stint of development to, we're trying to synchronize those as best as we can. And we front-loaded a lot on the Symphony side so we can do a similar pattern of design, build, and test on an even higher frequency level than we can with the airplane. So.
Okay, and you've had the demonstrator. I haven't seen your demonstrator. You had a...
Yeah, so we were fortunate to...
Where are you? And
to enliven the entryway post-registration with one of our subscale aircraft. So we were fortunate, given that we were working on a high-speed VTOL design, to be invited back in 2020 to compete in the Air Force High-Speed VTOL Challenge, which we won. And it so freaked out one of the other major competitors that they utilized their political muscle and actually killed the high-speed VTOL challenge. So we didn't actually get the prototype development contract that I think we had earned through our performance. So we're still out there competing. I believe we have a better vehicle architecture and a better team, but the primes have lobbyists and, well, they have lobbyists and they have subcontractors in every congressional district. So the fight is on. So we are competing for some of the future vertical lift programs in DoD. I think we're well positioned. We'll stay in that. And in the meantime, we're actually going to commercialize our subscales for counter UAS. And so we're still in the fight. And I think what that adds up to, if everything went ideally, you'd be able to buy a ticket for regional air mobility flight on one of our tilt wings in the 2032, 2033 timeframe.
All right, I'm looking forward to it. All right, so during this past robust discussion here, we've got a lot of questions coming in from the audience. And so the first one, what is the Natilus time plan for flight test, and how do you differentiate to Jet Zero, who had a pretty big presence here at the conference?
Yeah, I have to be very politically correct in this one, right? So Jet Zero has got a fantastic marketing team. I love them. With that being said, they, I think, are complementary to us, and that's the way that the airlines view that. If you look at our airplane, the Horizon, it's about 160,000 pounds, 155,000 pounds. They're 255,000 pounds. The difference between us and Jet Zero is they don't have a frickin' engine. Mic drop. So being politically correct, I just came back from the Pentagon, and I think that concern silos not only through me, but everybody in the industry.
Okay. All right. Let's see. This goes to David. What aspect of Boom's aircraft design enables the sonic boom to be refracted in the atmosphere? Is there a particular feature, or is it purely the atmospheric?
It's a great question. The beauty of the concept of Mach cutoff is that you can fly any aircraft supersonic, and the atmosphere does the work for you. As long as that airplane is flying within the narrow band of cruise Mach number that the atmosphere allows you to accomplish that Mach cutoff operation. If you're a little bit faster, the altitude of where the refraction occurs, where that inflection point occurs, gets closer and closer to the ground until it touches the ground. And that can change every day by the hour or even faster where we have strong gradients, temperature inversions, and whatnot. What I've seen is that we have the ability to sample the atmosphere now much better with greater resolution than we have ever been able to do in the industry. And so that brings the opportunity to better track what simply ends up being aircraft speed as a function of the atmosphere at a given point in time.
Is it going to change your flight path over land on a daily basis? I mean, do you have
that is an option.
Flight planning, or?
That is an option, and there are probably scenarios where that might make more sense than slowing down, which is the other option. If the speed control in the airplane is aware of its environment, then we can tailor things appropriately as a function of the environment. If we end up in a scenario that's extreme, you can always fly subsonic for a short time.
Okay, and over water, so you're designed to fly faster than the cutoff over water, and then you back off. So you have to be kind of multi-point optimum.
That's right, yeah. So we have one airplane to do many things. Over water, the difference is the sonic boom will reach the ground. This is not a low boom airplane design. That ends up at a very different place in the design space with very different trades between performance and noise. So to manage the sonic boom in that case, we have the intent, and we have some demonstrations in-house at least, of how we route between city pairs while managing the primary boom carpet that reaches the ground, but also estimating secondary booms and where those can potentially land. We've seen in even presentations this week on how unique the secondary boom behavior can be as a function of atmosphere, going east to west and vice versa, and across different city pairs. And so we're mindful of that and baking that into the operations in order to avoid the much stronger primary boom from falling on populated areas.
Yeah. Kyle, are there any environmental limitations for Otto's laminar flow concept? That is, airborne pollution, bugs, location access, operations,
Yeah,
all the usual,
all the typical questions.
That,
Yeah, absolutely. So there's a couple of really interesting things. So first of all, laminar flow design does not mean we're designed to have full laminar flow on our airfoil and on the nose of the aircraft in all phases of flight. In fact, the aircraft is also designed to fly just fine in turbulent flow, which is actually a really practical part of our path to certification, right? Is that it's safe to fly in all regimes.
Yeah.
We are optimizing our laminar flow performance for that, 45 to 51,000 foot cruise range. I mean, that's really if you said, of course, the aircraft has to fly everywhere, but the point optimization is up there high. Yeah. When you go high, there's a couple of really interesting things that happen. So obviously, the air is getting thinner, your Reynolds number is coming down. What we found in our wind tunnel testing, we've leveraged multiple different wind tunnel tests now, as well as our demonstrator aircraft, that as you go high and that Reynolds number comes down, the susceptibility to trip the flow on any sort of imperfection, so that is dings, dents, scratches, steps, gaps, fastener heads, bugs, is reduced significantly as you go high. Even the difference between 45,000 feet and 51,000 feet is a big difference. And typically, your turbulent business jets don't fly up that high because there's not a huge performance benefit from it. If you're in turbulent flow, boundary layer thickens, you pick up more drag. From a laminar flow standpoint, as you go higher, you actually get longer runs of laminar flow that are more robust. So it's desirable to get up high. Now, that said, Otto is sizing for that super mid mission, right? So stand-up cabin, 3,200 mile range, that gets you westbound from Miami to Seattle or Boston to San Francisco. A couple interesting things happen there as well. As you go higher, your headwind going westbound is reduced into the order on average by about 20 knots between 45,000 feet and 51,000 feet. So one, we can go faster. We can also get farther with less range, if you will, from a spec standpoint. But also, from a biz jet standpoint, you look at lights, mids, super mids, and even large cabin jets, the average mission is not 3,200 miles. The average mission for all of those jets is about 1,000 miles with 2 passengers. We'll do that all day, whether we're laminar or turbulent. Whether you fly us to 51,000 feet or you want to go fly to 35 or however you're routed, we'll make 1,000 miles, no problem. And the beautiful part is we're doing that with a 19,000-pound jet instead of a 40,000-pound jet. So even if we're not flying in our perfectly optimum cruise configuration, we're still carrying half the weight and burning half the fuel. So that's the really cool part, is that laminar flow cruise performance lets us meet that long-range mission, which, by the way, we talked about Part 135 of operations. Otto's current leadership was founder of, Paul Tao was founder of ExoJet, which is now VistaJet. Their fleet was Citation 10s and Challenger 300s and 350s. Super mid was their bread and butter. Looking at their operational data, less than 5% of flights were over 2,600 miles annually. Now, that doesn't mean that you have to not do those flights. If
Yeah.
you want to have
Well,
a complete fleet, you have to do it.
The key thing about that is a lot of those purchases are determined by what I call the 10% flights.
Yep.
So I spent time in business aviation.
Yep.
And so having that long range is hugely important as the final deciding factor.
Yep.
So that's a key for you guys.
What does that mean operationally? What we found operating the 500, wipe the wing down before you fly, which on a super mid-sized business jet is not a hard thing to do. Make sure it's clean. I mean, the Piaggio operators will tell you the same thing, right? If you want, there's even a knockdown in the AFM for it, right, for a dirty airplane. It's not that big a deal, though, to go wipe it down, make sure it's clean before you go.
You look like you want to say something.
Yeah, so the alternate mid-size category of jets is very fascinating. It's not about the range, it's about the porta potty, really, when you come down to it. Because the average mission profile, we've done a lot of studies when we were working through the industry, is 2.5 hours. And 2.5 hours is when you want to go take a leak.
Yeah, you need a nice lav.
Yep.
So you could have miles, range for 1,500 nautical miles, but nobody gives it.
Well, that's the beautiful thing about what we're doing with Otto is we have that super mid-size cabin at the light jet weight. And I think that's going to be a huge selling point. The cabin, we've got some spectacular mock-ups at our facility in Fort Worth. They'll be starting making the rounds soon.
In there?
We've got a great lav. If that's, I know that's a concern, but
And by the way,
a great lav.
By the way, we've designed our aircraft so that you can have 2 pilots with a separated cockpit and a full lav with a galley and a closet and still seat 6 people, and it's handicapped accessible.
So just back to laminar flow for a second. So flying high, great. Takeoff and landing, where are the bugs? Are you having to do any kind of coding or anything?
So we are looking at, both from just a general operations standpoint, coatings that would help with bugs not sticking and making it easier to clean. And there are a few options out there, but that's not we don't see that being as a practical limiter for our operations. Now, in a worst case scenario, let's say you are flying that long range mission and you've got a big headwind and you take off and you fly through a bunch of bugs. Practically speaking, what happens then? Yeah. Worst case scenario, you're going to make a tech stop somewhere along the way, which is, your passengers may not love that, but we're talking about such a small percentage of those missions, we really don't see that as being a fundamental showstopper for the configuration.
So you also addressed one of the questions that I always get, and that's laminar flow airplane, what if it's turbulent? You may not be able to answer this, but what sort of performance hit? Do you just fly a shorter range if you're going to be turbulent, or how do you?
Yeah.
What sort of magnitude is that? People ask that a lot.
Yeah. So generally speaking, what we've found is it's in. We've said that we get about a 25 to 30% benefit from our laminar flow runs. If you somehow magically turned off the laminar flow, which we do analytically, right? Yeah. It's in that 25 to 30% hit, and that comes both from a range, speed, and fuel burn hit. Now, if you don't care so much about the range piece because you're flying 1,000 miles, and you don't care so much about the fuel burn, so you're willing to just push the throttle forward a little further, then that's not too big of a deal. So for our Part 91 operators, they may or may not care about how much laminar flow they get on the aircraft. For the fleet operators, and you start talking about the big guys, the NetJets, the FlexJets, the VistaJets, you guys know the names of those folks, right? When you start looking at big fleets, you want that airplane to be clean because that fuel burn reduction is a huge part of what makes whether or not you're profitable, right? So.
All right, one for Peter here. Regarding the no airports vision, will operations be set up to replace TSA? How will safety and security be mitigated?
Great question. So there's 2 answers to that. With the current security regime, we won't have to put people through TSA screening because the aircraft is small enough that you don't have to do that with the wanting. We do have to check the no-fly list, and people do that. You have to do that today if you're operating Part 135. It's possible it could change in the future, in which case we'll have to pay to have a TSA screener and a scanner and somebody wand you. So it shouldn't be a big deal either way, really.
Let's see. This could maybe, as we were talking about propulsion, and there's different comments we've heard about propulsion. So, what testing requirements are there for validation of the various new engine concepts and integration challenges. And so I think this is an opportunity we have an engine, we're working on an engine. Where do engines stand and how do you integrate and work with
maybe I'll start.
Or new engine companies?
Yeah, and so we have a very fundamental kind of like thought through this. You never put a brand new engine in a brand new airplane. If you do that, you will destroy every single program. We've seen it with the L-1011. We've seen it countless times and times and over. There are corner cases.
David, we're rooting for you.
We're rooting for you. We're 100%.
But we are also team off the shelf, absolutely.
Yeah. So there are times when you have to do what you have to do. But that's kind of like the way I would look at it, is you have to do what you have to do to get it working.
Anyone else?
Yeah, there's a different sensitivity when it comes to the matching of an engine and an airframe, depending on what you're trying to accomplish in a mission. And I think at low speed, the sensitivity is not as high, potentially, as it can be for high speed. What I've seen as we brought together the turbo machinery designers, the propulsion system designers, and integrated that onto the Overture designs, we saw large swings in performance as we would play with the design part of both of these things. And we found that there were corners of the design space that we weren't even aware of until we started exploring different combinations of parameters, looking at constraints for noise and other aspects of integration. And in our case, as you mentioned, it could be a unique case where in order to overcome the stronger sensitivity between off-the-shelf and matching an airplane, where it becomes a much stronger struggle to close that. In our case, we found it was worth the gamble to go ahead and design the engine to be just right for that. Because, as you mentioned, you have to do what you have to do to close the entire, not just mission case, but the business case. And in order, again, being mission focused, there didn't seem to be any other way to pull that off.
So I have a question for you, to be honest. So when I looked at the original boom concept, I really fell in love with it. It was 3 engines. Now you look exactly like the Concorde. Like, what do you fundamentally think is fundamentally like different aerodynamics or the engine that's going to actually propagate the concept forward?
Yeah, so we can talk for hours on the differences and all of that. I'll try to just pick a few that come to mind right now. There's a difference in flying with and without afterburners, for example. In order to meet the LTO noise regulations, we cannot rely on afterburners to get off the ground. That's a major game change to do that. But to accomplish that in a traditional way with off-the-shelf components, you actually might penalize your high-speed performance too much. And this is where finding that delicate balance between the ability to meet low-speed regulations and constraints and the high-speed performance we needed, that's where we found the high sensitivities. I think that on the aerodynamics side, I'm much more familiar with that piece. We've iterated and traded a variety of concepts before I arrived with different numbers of engines. We found that there are multiple solutions to the design problem, of course. But where we landed actually became a balanced view on the passenger experience part, what the cabin looks like. We looked at operations, we looked at the way we're keeping noise down, and we were able to find that we didn't have to sacrifice as much high-speed performance as you otherwise might need to just to meet your low-speed constraints. We've approached that tension in design a different way than I've seen done in the past, and that's where I see the opportunity to actually unlock changing the fleet, so to speak, in ways Concorde would not have been able to do today.
I'd like to riff off this question a little bit. Sometimes we get asked, if this is such a great business, why don't people do it with helicopters today? And it turns out the answer is helicopters are too slow. So we are using off-the-shelf engines with a proven tilt-wing vehicle configuration, but our goal was to cruise at comparatively high speed, not supersonic, but 420 knots at 20,000 feet. That is a trade space in VTOL that apparently no one else had ever explored. And it's interesting. So our DOC models out at 50% higher per hour than a comparably sized helicopter, like an AW139. But because we go 3 times faster, it's actually half as much per mile. So there's a cost savings advantage to speed with our vehicle configuration and the virtue of a wing. The other thing that happens is when what sizes our power plant is the top speed case, and we end up with way extra power in the hover, enough so that we can, one engine inoperative, we can meet the FAA Class A regulations for climbing out. But in the military case, what's really interesting is we have megawatts of available power in the hover for things like inexhaustible countermeasures. I talked about point defense lasers with SOCOM thinking I was joking, and I found out they were already working on that for the C-130. So there's a thing about innovating where you take known quantities and combine them in novel ways to achieve new points in the trade space. And that's really where we have been living. We've been trying not to invent anything we don't have to, but innovate actively.
All right, I'm going to kind of off of trade space. Currently the top-rated question came from an 8th grader. Has been voted up by the audience. Do you think there will be a time when blended wing designs can become supersonic?
No.
So.
No. Straight up, no. The answer is, because we actually already asked the same question to ourselves. We had a major airline customer that actually asked the same question as well. And we were sitting in like senior technical space, and they asked us, can you actually make this supersonic? And we looked originally at Led Neisser's paper, and we were like, if we do this, this, and this, and this, we can make it supersonic. And that felt really good to us. And then they were like, well, the next question is, can the engine manufacturers do it? And so we started talking to the major engine manufacturers, and they said, pardon my French, but fuck no. Like, they said, like, if you're going to go supersonic, it's off design point, and you have to replace the engines every single year.
Yeah.
So, like, we as airframers could do so much more, but the engine manufacturers are so far behind.
Sounds like you need your own engine.
Oh.
Have you talked to David?
Were there any blended wings in your design space early on?
That's a great question. I'm not sure. I've seen the progression of the design concepts, and I don't see any that
I don't
resemble
remember
that.
seeing one. So.
No, I know. I've known Blake for a long time. There was never a question about that.
Yeah. But the other blended wing question, so you've Kona and Horizon. Horizon's pointed at single aisle. I don't remember what you said cruise speed was, but single aisle speed. How high a speed do you think you could push?
The configuration could be pushed up to Mach 0.94. The engines cannot be pushed past Mach 0.8.
Okay, all right.
It's an engine question, it's not an airframe question.
Okay, all right. I think this is a good one for all of you. In aviation, software has become a large cost and seems to keep growing. This seems like a concern exacerbated by these concepts.
Can I start? Sorry.
No, you can't.
I have to take this one. So, so when I used to work military programs, there was like something called a software line of code cost $1,000 for an autopilot. $1,000. That's if you're going to do military-style hardware. That's what it costs. Like it's called like there's like a really nice acronym for it. I've been asking the same question for a very long time from the industry. Like, what does a fly-by-wire system cost in software?
Yeah.
And I've had numbers thrown at me from 1 to 2 billion to 400,000. So the answer is from a anybody can write a line of code and make it work. Question is it a certifiable line of code? And I would love to get an answer from all 4 of you.
So
I asked all 4, so
Yeah.
software.
Go down the line.
So we can go down the line. So having been involved with multiple fly-by-wire development programs in the rotorcraft space, granted, 609, 525, V-22, there's a trope in the industry, and it's pretty true. Software is always late. Software is always last. Now, the software guys are going to raise their hands and say, whoa, 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 we're always giving our requirements last, so that's what makes us last. And everyone thinks you can just fix it with software, so that, we're the get-out-of-jail-free card, right?
Yeah.
And that is true to an extent. But, it comes back to the program cost topic when we said, how much does a program cost? Well, if you look at the trends for program costs, the number one trend line for what a program costs is how long the program takes.
Yep.
Because when you're ramped up at the tail end of a program, you could easily be burning $100, $200, $300 million a year, depending on the size of the program. And if you start taking delays due to the poor software guys always get the tail end of this, but it gets blamed on software. Well, you're riding that whole program cost on that tail end.
Yep.
So the question, and I agree with your answer on that, it can vary wildly. It could absolutely be billions of dollars. There are plenty of programs that have spent billions of dollars chasing this. I think a big part of that is how long it took to do it.
Wait. So kind of going on the same logic, I have to ask the same question. Like if I give you a week,
You'll get an answer in a week.
is it a good answer?
It's going to be a weak answer.
Well, so,
Is that
so I have to pipe up as the software guy in the panel. So my undergraduate degree from MIT was computer science, and I spent the first 2/3 of my career in software and networking, not in aerospace software. Literally the first senior executive my co-founder and I hired is our chief software officer, who has software running on B1, B2, F-18, F-35,
The most
F-22.
expensive softwares in the world.
Yes, and it's safety critical software on those platforms. So here's the key. You have to understand DAL-A. You have to understand the process. You have to know how it gets done. But there's also a reality in the software world that was figured out about 40 years ago and is still true. That is, the most productive software engineers are 10 times better than the average, and the average software engineers are 10 times better than the worst. And getting back to the point about ramping up programs, there's an entire ecosystem out there of contract engineering groups that support aircraft programs, and they shift from one to the other as they ramp up and ramp down. We're not all hiring those people in-house. We're contracting with these groups. Those groups are primarily made up of average and worst software engineers. So the key is, if you want to control this, is you have to be able to attract enough of the best to be able to contain your schedule risk on this. And you've got to be working on it from day one. That's how successful software programs work.
I think the other I'll add to that is you have to be laser focused on what from day one in your requirements of what you're going to do with the software and what you're not going to do with the software. I know like one of the earliest trades that Otto did for our current Phantom 3500 development was, are we going to be fly-by-wire or not?
Yeah.
Right? And there are certainly benefits from fly-by-wire standpoint. You know, relaxed stability, load alleviation, SVO opportunities in future. If and when we do a Part 25 program, which, you know, when we're successful with this one, that'll be next. Fly-by-wire is absolutely on the table. The choice was made for this program to go with mechanical controls to limit that software development risk as it pertains not only to the cost of doing the software, which again, I totally agree, you have to do right from the beginning, but also to mitigate risk of delays due to certification, because there's still no certified Part 23 fly-by-wire, or 27, or 29.
Oh, that's
Phenom.
Oh no.
The legacy
Phenom,
for
Phenom,
the legacy
vertical
450.
tails and the Phenom, yeah, like
Yeah.
come on.
Not the whole airplane.
Not the whole airplane.
No,
You know why?
What is it? The legacy 450.
The risk is
Now the
the
Praetor
cost.
500.
Those are 25.
The
25?
only
Those are Part
company that has
25,
actually
right.
been able to nail down fly-by-wire risk is Embraer, and they're not here. So they are the only ones that actually have a number.
That's
It
fair.
doesn't change the position that as you look for a full fly-by-wire aircraft, there is no Part 23, 27, or 29 aircraft
There's pieces
certified.
of it.
There's pieces. I don't disagree.
Oh, no, you're absolutely right. And I think it's brilliant to go to market without. I wish I could. Very, very early on, I managed 3 takeoffs, no hovers, with 3 throttles and 3 collectives manually in the sim. You really need auto stability in a VTOL aircraft.
Well, I mean, look at XV-15 to 609 and V-22. XV-15 was not fly-by-wire.
Right.
It doesn't make sense practically for a tilt rotor application. So I totally agree with you.
Yeah.
And if you're going to do it, you got to do it right from day one. So
I agree with that.
100% there.
I love it when these questions generate more questions. David, do you have any thoughts on that, or?
You guys fly-by-wire or no?
Not much to add. Not much to add on that. I think we see the benefits of fly-by-wire. We look at beyond beyond that alone, though. I think that granular question of how do we bring the cost of software down, we're asking that same hard question, and trying to actually dissect it into what are the pieces of effort that roll up into that big number. And we're trying to see, are there ways to work with the providers? Because we've seen similar trends as you have seen. It really depends on who you're working with. and how that can lead to a wild swing in costs. But it also has a dependency on the statement of work involved behind what they're doing. And that's where we might have some flexibility. Not sure all the flexibility we need to bring the numbers as far down as we would like, but we're at least trying to tackle it from that angle.
Yep.
All right, there's two questions that are very similar, and they point to Peter. I think you were talking about ticket prices, and the question was whether the ticket prices you were talking about are for the future or what it would be at entry into service, and you would expect them to come down over time, that sort of thing.
Those are today's dollars.
Today's dollars.
So project inflation forward, but the
is there a premium for initial entry into service, and then is it for?
No, so those numbers I showed there are based on a 10-year, month-by-month detailed model of our airline operations that I made because I'm insane. It's actually because I wouldn't believe that it worked until I did that detail. So I took the operating model that we had at Linear Air, our 135, and I expanded it to cover 135 commuter operations. And it has everything. And there are a lot of surprising things that come out of that I would love to flame about, but we don't have time. So I'm confident that those numbers are as accurate as they can be. And as you project into the future, there's no reason that the ratio of those door-to-door costs to current ground travel, air travel, ground travel that we're competing with is going to change. So, and the key thing there I need to point out is on these regional routes, the demand I'm going after is symmetric business travel for the entry into service. And our key method for entry into service, and I probably shouldn't even say this, but I will, is we will pre-sell 75% of the seats a year in advance on a route to corporate customers in bulk before we enter service on that route. That will cover all of our direct operating costs and all the overhead. There's no profit in that. The profit comes from that as 25%, which we can then sell via the internet in various ways, and we can do all kinds of cool discriminatory pricing. We do surge pricing, we can do this, we can do that. But we've got this core baked in. Unless anybody think that's been practical, that is in fact how large corporations buy air travel today. They put out tenders for a year or 2 years in advance. So,
yeah, David, do you want to say something about the ticket price and the strategy there on Supersonic?
Yeah, so as I showed in one of the slides, as we've surveyed the public, there seems to be an appetite to pay a premium for speed. In the past with Concorde, the price tag was high enough that it locked out the majority of the population, except for those who were celebrities or the ultra-wealthy. And even some who would somehow save their dollars to do what I think was called the lifetime flight or something like that. It was the once-in-a-lifetime experience. We've seen that now the business class part of the market is already a premium. And that is our initial going-in position to address that market. And there is apparently an appetite to pay a 50% roughly premium on speed because their use case is different. Right? For many who have traveled the world for business, you find that it gets tiring. And having that premium for speed means something after your third, fourth, fifth flight, much more than maybe the first flight. And so we believe that keeps the price tag within range, and it makes sense. And if we look far down in the future, our ultimate goal is to be able to improve the technology so that it's not just business class travelers that benefit from it.
All right, so we're nearing the end here. I'm going to ask one more technical-ish question to Kyle, and then I'm going to go down the row so you can start thinking about it. You know, for your vision, what do you see as your maybe greatest challenge, and why are you optimistic that I'm going to be able to buy that ticket? Otto, with the altitude at 51,000 feet, do you foresee any certification problems with cabin pressure, and does your concept scale from business class to single aisle?
Yeah, okay, so two questions there. So first of all, 51,000 feet, we do have to pull in special conditions from Part 25. The cabin pressurization factor goes from 1.33 to 1.67 to handle that. We are a composite fuselage. We're designing for those factors. We don't see an issue there. maybe the bigger technical issue that we're working through, or we have a path forward for, is emergency descent requirements, because of course you need to get down below 41 pretty quick, and with a really slippery airplane, that can be challenging to do. So that's maybe the biggest challenge up there. But our engine's already certified to 51, and there are, Sino engine, Cyberjet did the same thing, so we don't really see a certification risk around that. Just got a size for it. And then the second question was
Single aisle.
Yeah, single aisle. So, that's a really interesting question. So we've been studying that. There are diminishing returns from our core technology on that practical implementation of laminar flow. There are diminishing returns as you get larger and larger from a scale factor standpoint, and from starting to make considerations around things like how do you keep laminar flow past a leading edge device, which you need on those larger aircraft if you're looking at like a cube square sizing of the aircraft, right? That said, we definitely see benefit in like the large cabin and smaller regional spaces. So that is a pretty, in our opinion, pretty clear next potential market. There's market to go smaller as well. In fact, the 500L is a great airplane, right? There would be potentially an opportunity to go after like, the PC-12 type market, single turboprop market if we wanted to go down. But what we're really interested in is we start looking at that, back to the regional discussion. We're not going to take off vertically, not in Otto's current plan, but when we start looking at competition between regional jets and single aisle, the regional jets are much worse per seat mile, gallons per seat mile. We don't need to be as good as a single aisle. As long as we get better than the existing ones, it starts to unlock more point-to-point flights, which is better from a carbon emission standpoint because you're flying a more direct route. And from a customer standpoint, customers prefer to have more direct flights and more direct flights. If you can offer multiple flights per day, your customers are willing to pay more for them. So we actually see unlocking the economics around regional jets with this technology.
All right.
So that's how we would compete with the single aisle space.
All right. So in maybe a minute each.
Yep, sorry.
It's all right. No, that's all right. That's why are you optimistic, and what's your favorite or biggest challenge?
Well, I'm optimistic because we have example aircraft that have flown before, and we've just optimized it and made it better. So it's not like it's impossible or anything. We know they can fly, and it will fly. So our challenge is an economic one rather than a technical one. We are depending on highly engineered composite propeller blades, and we know they'll work for a while. The question is, will they work for long enough that the expense won't be a challenge for us?
All right. David.
Yeah, as many have already experienced, and I'm sure everyone on the panel, certifying an aircraft is a large undertaking, and that could be one of the most difficult parts of the overall development process. For Boom, after over a decade of working high-speed vehicles, with all of the best fidelity we can, I'm confident that we have a design that can work and close. And scaling that up to the hardware is always the hard part, and that's what we have ahead. And doing that with the resources we have is also part of that challenge. We're not assuming we're going to have a massive army of engineers to pull it off. And so I'm optimistic that our approach at trying to disrupt the process first is going to be the big enabler there.
Kyle.
Most optimistic? I think we've got a really clear path to our product.
Yeah.
In Part 23, great business case in an existing market. That's what I'm excited about. I'm excited about getting the first one flying and getting it certified.
And you have a big challenge you fear?
The devil in the details.
Devil in the details.
I mean, I came out of the eVTOL world previously. I could tell you 6 different terrifying challenges from there.
Okay.
I don't have a single one at Otto that is just keeping me up at night other than all of the little things.
All the little things, yeah.
The weight and drag creeping in, right?
And final word.
I guess would be supplier-based manufacturing. We're all competing for the same manufacturing. So like whether it's Boom, Otto, and everybody else, carbon fiber is always going to be top of mind. So we buy in bulk, we always do, but there's only 2 suppliers in the world. So just whoever gets there first and who has got the biggest amount of pocketbook. So that's always a big idea.
All right, well, I'm looking forward to buying tickets from each of you in the not too distant future. I want to thank the audience first for being around here on Friday and participating, and let's all thank our panelists. Thank you very much.